Welcome to this video where we'll solve the problem number 1844, replace all digits with characters. In this problem, we'll explore an interesting string manipulation task where we alternate between characters and digits to transform the input string. Let's dive in. In this problem, you are given a string S that alternates between lowercase English letters and digits, starting with a letter. The string's length is always even, which means every letter is paired with a digit. For instance, at any valid position I, if I is even ES, I will always be a lowercase letter, and if I is odd, S, I will always be a digit. Your task is to replace each digit in the string with a new character, determined by shifting the preceding letter forward in the alphabet by the number of positions specified by the digit. For example, if a letter S, I1, is at and the digit S, I, is 3, the replacement character becomes D, since shifting it forward by 3 steps results in D. The goal is to return the modified string after applying this transformation to all digits in S. The input to this problem is an even-length string S that follows the described structure, lowercase letters at even indices and digits at odd indices. The output is a string of the same length in which each digit has been replaced with its corresponding shifted character, while the letters remain unchanged. Let's look at a few examples to better understand how this transformation works. Consider the string S equals A1C1E1. In this case, each digit is replaced based on the shifting rule, and the final output is ABCDEF. Here's how the transformation works step by step for the string S equals A1C1E1. First, at index 0, we have the letter A, and at index 1, the digit is 1. Shifting A forward by 1 position gives B. Next, at index 2, the letter C is paired with the digit 1 at index 3. Shifting C forward by 1 results in D. Finally, at index 4, the letter E is paired with the digit 1 at index 5. Shifting E forward by 1 produces F. Combining all these transformations, the final string becomes ABCDEF. Now, let's look at another example. Take the string S equals A1B2C3D4. At index 0, the letter A is shifted forward by 1, resulting in B. At index 2, the letter B is shifted forward by 2 to give D. At index 4, the letter C is shifted forward by 3, resulting in F. Finally, at index 6, the letter D is shifted forward by 4 to produce H. Putting it all together, the final string becomes ABCD. This demonstrates how digits in the string dictate the transformation of their preceding letters. Now, let's discuss a few important constraints and edge cases. The string length S.length is always between 1 and 100, and it is guaranteed to be even. Lowercase letters occupy even indices, while digits are at odd indices. When shifting a letter, if the result goes beyond Z, it wraps around to the beginning of the alphabet. For instance, shifting Z forward by 1 results in A. For a zero shift, such as when a digit is 0, the corresponding letter remains unchanged. For example, if the input is S equals X5Y0Z9, the output becomes SYSD, as the shifts handle wrapping and zero shifts correctly. These details ensure you can handle all possible inputs confidently. To tackle this problem, we considered multiple approaches, starting with the brute force method. The intuition here is straightforward. Since the string alternates between letters at even indices and digits at odd indices, we can iterate through the string, identify the digits, and replace them based on the problem's transformation logic. Specifically, for each digit at an odd index, we calculate the new character by adding the digit's integer value to the ASCII value of the preceding character, which is guaranteed to be a letter. This new character is then appended to a separate result string. The time complexity for this approach is O(n), as we process each character in the string once, while the space complexity is also O(n), due to the creation of the result string. While this method is simple and adheres closely to the problem's requirements, it doesn't take advantage of in-place modifications, which could save memory in other contexts. Nonetheless, this approach is easy to implement and debug, making it a strong starting point. An alternative approach involves optimizing for in-place transformations. Instead of constructing a new string, we can modify the original string directly in place, assuming the string is mutable, as it is in languages like C++ or Java. For Python, strings are immutable, so we would first convert the string into a list of characters, perform the transformations, and then join the list back into a string. The implementation involves iterating through the list, and for each digit at an odd index, we compute the new character in the same way as the brute force approach. This computed character replaces the digit in the list. The overall time complexity remains O(n), as each character is processed once, while the space complexity in Python remains O(n), due to the temporary list. This method can reduce intermediate memory usage in languages with mutable strings, but in Python, the space requirements are effectively the same as brute force. Additionally, we explored using list comprehensions to make the code more concise. Here, we iterate through indices, appending the original character for even indices and computing the transformed character for odd indices. This approach also has O(n) time and space complexity but can be less readable and harder to debug compared to a traditional loop. For this problem, we ultimately chose the brute force approach due to its clarity and simplicity. Despite all the methods sharing the same time and space complexity, the brute force strategy stands out for being intuitive, easy to implement, and well aligned with the problem's constraints. Optimized in-place transformations, while useful in languages with mutable strings, do not offer any real advantage in Python due to its immutable string properties. Similarly, while list comprehensions allow for a more compact implementation, they can compromise code readability, especially for those new to the problem. Key observations that help simplify the solution include the guaranteed alternation between letters and digits in the string, which eliminates the need for complex index handling. The transformation logic relies on ASCII values, ensuring that adding an integer directly to a character's ASCII value produces the desired result. Additionally, the constraints of the problem ensure that the transformation will always remain within the bounds of lowercase English letters, removing the need for additional validation or edge case handling. When comparing the different approaches, the brute force method emerges as the most balanced solution. It is simple, clear, and easy to debug, making it suitable for most use cases. The optimized in-place approach can save memory in languages with mutable strings, but in Python, it does not offer any significant advantage due to the need for temporary list creation. On the other hand, the list comprehension approach, while concise, sacrifices readability and can be more challenging to debug when issues arise. Given these considerations, the brute force approach provides the best combination of clarity, simplicity, and efficiency for solving this problem, making it the most practical choice for implementation. To solve this problem, we start by understanding the structure of the input string. The string S has a length of n, and it follows a specific pattern. Letters are found at even indices, while digits appear at odd indices. For example, in the string S equals A1 B2 C3, the even indices 0, 2, and 4 contain the characters at B and C, whereas the odd indices 1, 3, and 5 contain the digits 1, 2, and 3. Once we understand this structure, the next step is to define the transformation logic. Each digit at an odd index must be replaced by a new character. The new character is determined by shifting the preceding letter forward in the alphabet by the value of the digit. For instance, if the letter is at and the digit is 3, the resulting character would be D, since shifting it forward by 3 steps in the alphabet gives D. To handle edge cases, such as wrapping around from Z to A, we rely on modular arithmetic combined with ASCII value calculations to ensure the results stay within the valid range of lowercase letters. Now that we've defined the transformation logic, the algorithm proceeds by iterating through the string. We use an index I that runs from 0 to n1. During this traversal, we handle each index based on whether it's even or odd. If I is even, the character at that position is simply copied to the result as is. However, if I is odd, the character is a digit, and we compute the transformed character based on the preceding letter. The calculation involves taking the ASCII value of the preceding letter, adding the integer value of the digit, and then converting the resulting ASCII value back to a character. Specifically, the new character is computed as CHR, ORD, previous_char, plus digit. Here, previous_char refers to the letter at index I1, and digit is obtained by converting the character at index I into an integer using int. As we process each character, we append the result to a list, which allows for efficient string construction. Once the iteration is complete, we join all the characters in the list into a single string using .join, result, and return this final transformed string as the solution. There are a few key insights that make this algorithm robust and efficient.
First, modular arithmetic ensures that transformations remain valid when shifting characters near the end of the alphabet. For example, if the transformation shifts Z by 2 steps, the result should wrap around and become B. This wrapping behavior is handled seamlessly by manipulating ASCII values. Next, the algorithm avoids performance pitfalls by using a list to store intermediate results. Concatenating strings repeatedly can lead to O(n)² time complexity due to the creation of new strings at each step. By using a list and joining it at the end, we achieve an overall time complexity of O(n). Additionally, the algorithm accounts for edge cases such as an empty string, which should simply return an empty output, or a string with a single character, where no transformation is required since there are no digits. Finally, when transformations involve wrapping, the algorithm ensures that the result remains within the range of lowercase letters, from A to Z, using modular arithmetic. To implement this efficiently, we rely on two key data structures and techniques. First, we use a result list to store transformed characters as we iterate through the string. This approach avoids the inefficiency of repeated string concatenation in Python, which would otherwise create new copies of the string during each modification. By constructing the output in a list and joining it at the end, we achieve optimal performance. Second, we use ASCII calculations to handle character transformations. The ORD function gives us the ASCII value of a character, and CHR converts it back to a character after applying the necessary transformations. This precise control ensures correct results, even for edge cases involving wrapping. Additionally, the algorithm is optimized to process the string in a single pass, achieving O(n) time complexity. By leveraging the guaranteed input format, alternating letters and digits, we eliminate unnecessary checks, further streamlining the process. For large inputs, we can pre-compute certain operations, such as modular arithmetic calculations, to further enhance performance. This Python implementation solves LeetCode problem 1844, replace all digits with characters. The goal is to transform a string where digits at odd indices represent the number of shifts to apply to the preceding letter. The solution involves iterating through the string, replacing digits with their corresponding shifted characters, and constructing the final transformed string. Detailed explanation. 1. Input conversion. The input string S is first converted into a list result for easier in-place manipulation. Strings in Python are immutable, so using a list simplifies updates. 2. Iteration over digits. We loop through the indices of the string, specifically odd indices 1, 3, 5, etc., because these contain the digits. The step size in the range function is set to 2, ensuring only odd indices are considered. 3. Character replacement. For each digit at index I, we calculate the new character by shifting the ASCII value of the preceding letter, at I1, by the numeric value of the digit, converted from string to integer. This is achieved using the expression CHR, ORD, SI1, plus int, SI, where ORD, SI1, retrieves the ASCII value of the letter. Int, SI, converts the digit to an integer. Adding these values gives the ASCII code of the new character, which is then converted back to a character using CHR. For updating the result, the calculated character replaces the digit at the current index in the result list. 5. Final string construction. After processing all digits, the list result is joined back into a string using .join, result, and returned as the final output. Complexity analysis. Time complexity, O(n), where n is the length of the string. We iterate through the string once, processing each digit in constant time. Space complexity, O(n), as we create a list of the same length as the input string. This approach is efficient and adheres to the constraints of the problem, handling all edge cases such as empty strings or strings with minimal length, e.g., A1. The code is concise, clean, and easy to maintain. This is the Java implementation of LeetCode problem number 1844, replace all digits with characters. The code mirrors the logic of the provided Python solution. It processes the string by iterating through the odd indices, which contain digits, and replacing them with the shifted characters. Key differences include explicit type declarations and use of Java-specific constructs like char for string manipulation. To solve this problem, we start with the input string s equals A1C1E1. Since strings are immutable in Python,
we first convert the string into a list named result for easier manipulation. This gives us result equals a 1 C1 E1. Now, let's process each digit in the string one by one. In the first iteration, with I equals 1, we identify that the character before the digit is S, I1 equals a, and the digit itself is S, I equals 1. To calculate the new character, we take the ASCII value of a using ORD, add the integer value of the digit 1, and convert the result back to a character using CHR. This gives us CHR, 97 plus 1 equals B. We then update result 1 with this new character, so the list becomes a B, C, 1, E, 1. Moving to the second iteration, with I equals 3, the character before the digit is S, I1 equals C, and the digit is S, I equals 1. Using the same calculation process, we find that CHR, ORD, C, plus int, 1 equals D. We update result 3 with D, resulting in the updated list, a B, C, D, E, 1. In the third iteration, with I equals 5, the character before the digit is S, I1 equals E, and the digit is S, I equals 1. We follow the same process to calculate the new character, which is CHR, ORD, E, plus int, 1 equals F. We then update result 5 with F, and the final state of the list becomes a B, C, D, E, F. After completing all iterations, we convert the list back into a string using .join result. The final output for this example is the string ABCDEF. Now, let's look at the second example, with the input string S equals x3y4z5. As before, we start by converting the string into a list for easier manipulation, result equals x3y4z5. In the first iteration, with I equals 1, the character before the digit is S, I1 equals X, and the digit is S, I equals 3. Using the same calculation method, we compute CHR, ORD, X, plus int, 3, equals CHR, 120 plus 3, equals. We replace result 1 with the new character, resulting in X, Y, 4, Z, 5. In the second iteration, with I equals 3, the character before the digit is S, I1 equals Y, and the digit is S, I equals 4. The calculation gives us CHR, ORD, Y, plus int, 4, equals. Updating result 3 with transforms the list into X, Y, Z, 5. In the third iteration, with I equals 5, the character before the digit is S, I1 equals Z, and the digit is S, I equals 5. The calculation here results in CHR, ORD, Z, plus int, 5 equals CHR, 122 plus 5 equals CHR, 127. This gives us a non-printable character, which is still valid in terms of ASCII computation. We update result 5 with this computed character. Finally, we convert the result list back into a string using .join result. While the output string is correctly formed, it includes non-printable characters due to the ASCII value exceeding the printable range. This highlights the importance of considering input constraints when working with such transformations. The time complexity of the solution is O(n), where n is the length of the input string S. This is because the operations performed scale linearly with the size of the input. First, when the input string S is converted into a list using list S, each character is copied into the new list. This requires iterating through the entire string and takes O(n) time. Next, the for loop iterates through the odd indices of the string, such as 1, 3, 5. Since the loop increments by 2, it performs approximately n/2 iterations. For each iteration, several constant time operations are performed, such as accessing the previous character, converting the digit to an integer, performing arithmetic operations, and assigning the result back to the list. Each of these steps has a time complexity of O(1). When you sum up the iterations, the total cost of the loop becomes O(n/2), which simplifies to O(n). So far, these steps contribute linearly to the runtime complexity of the algorithm. Once the list has been updated with the modified characters, the final step is to join the list back into a single string using the join operation. This step also takes O(n) time because every element in the list is concatenated to form the resulting string. When we combine all the steps, the overall time complexity of the solution is O(n plus O(n plus O(n) equals O(n). For space complexity, the algorithm requires O(n) space due to the creation of a new list result that stores the modified characters. This list has the same length as the input string, which directly contributes to the linear space usage. In addition, the loop uses a few temporary variables, such as I, S, I1, and S, I, which only require constant space O(1). The input string itself does not consume additional space, as it is already provided. Overall, the dominant factor in space complexity comes from the result list, leading to an overall space complexity of O(n). When comparing this optimized solution to a brute force approach, the key difference lies in the efficiency of string manipulation. A naive approach might manually construct the resulting string character by character without using a list. While the time complexity would still be O(n), this method would involve repeated string concatenations, which are inefficient in Python. Specifically, concatenating strings using operations like result plus equals char can take O(n²) time in the worst case because Python strings are immutable. Each concatenation creates a new copy of the string, making the operation increasingly expensive as the string grows. The optimized solution avoids this overhead by using a mutable list to store intermediate results, minimizing the cost of repeated operations. As a result, it achieves the same O(n) time complexity with much smaller constant factors. In terms of best and worst case analysis, the time complexity remains O(n), regardless of the input because every character in the string must be processed. The algorithm performs the same operations on each character, ensuring consistent linear scaling. Mathematically, since the algorithm performs a constant amount of work per character and there are n characters in total, the total work is directly proportional to n, confirming that the time complexity is linear, O(n). In this section, let's explore some common mistakes developers encounter when solving this problem. One frequent issue is not handling edge cases properly. For instance, inputs with minimal lengths, such as an empty string or a string with just one character, are often overlooked during testing, which can lead to runtime errors. Always ensure you account for boundary cases to make your implementation robust. Another common mistake is incorrect index access. Since the problem often involves alternating between characters and digits, it's easy to accidentally access out-of-bounds indices if the bounds aren't carefully checked. A third issue is assuming the input always meets the problem's constraints. For example, if the constraints guarantee alternating characters and digits, there's no need to include extra validation steps in your code. Doing so not only wastes time but also adds unnecessary complexity. Finally, many overlook the potential for in-place solutions. Instead of creating additional data structures, modifying the string or array in place can significantly reduce space complexity. Always consider whether an in-place approach is feasible when optimizing your code. Inefficient iteration is another common pitfall. Using nested loops unnecessarily, such as for replacing or validating characters, can increase the time complexity from O(n) to O(n²), which becomes problematic for larger inputs. Aim for single-pass solutions whenever possible to maintain efficiency. Now, let's consider some insights that could help you in an interview setting. Problems with alternating patterns, such as characters and digits or zeros and ones, often benefit from modular arithmetic. For instance, I%2=0 can quickly identify positions for characters versus digits, simplifying the logic. Additionally, interviewers might challenge you to optimize your solution further, such as reducing space usage. Be prepared to adapt a two-pass solution into a single-pass in-place version. It's also crucial to clarify constraints with the interviewer. If unnecessary validation can be skipped, removing it saves time and simplifies your solution. Lastly, remember that your approach should be adaptable to variations of the problem. For instance, the pattern might involve alternating vowels and consonants or uppercase and lowercase letters. Being flexible in your logic will make your solution versatile. There are also several related problems on LeetCode that can help you practice similar concepts. For example, LeetCode 925, long press name, focuses on iterating through two strings while adhering to specific constraints. LeetCode 266, palindrome permutation, deals with character frequency and validating certain patterns, which can help you develop skills for handling character-based logic. Another related problem is LeetCode 1221, split a string in balanced strings, which revolves around alternating or balanced patterns.
This can reinforce your understanding of modular arithmetic and counting techniques.
Finally, LeetCode 186, Reverse Words in a String 2, is a great example of a problem requiring in-place string manipulation. These problems share overlapping concepts with the current challenge and can help deepen your understanding of efficient string processing and alternate pattern handling.
When it comes to alternative approaches, there are trade-offs to consider. A brute force approach might involve iterating through the string multiple times to ensure characters and digits are in the correct order. While this method is straightforward, its O(n)² time complexity makes it inefficient for larger inputs. A more optimized solution involves single-pass iteration, where you can use two pointers or modular arithmetic to ensure alternation as you traverse the string once. This reduces the time complexity to O(n). For space optimization, in-place modifications can be a powerful technique. Rather than creating a new string, you modify the input string or array directly, reducing space complexity to O(1). However, managing indices carefully is critical to avoid introducing bugs. Lastly, for problems that require specific ordering rules, stacks or queues can be helpful. These data structures allow you to reorder elements effectively, though they come at the cost of increased space complexity, typically O(n). Each of these approaches has its pros and cons, so it's important to choose the one that best balances efficiency and clarity for the given problem and constraints. Great job completing this problem.
To summarize, we used an efficient approach to manipulate the string while maintaining a linear time complexity.
Remember to practice similar problems to strengthen your skills.
Thanks for watching, and don't forget to like, share, and subscribe for more content.
That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions.
Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have.
Thanks for watching, and happy coding!